What is compression? Data compression is the act of encoding data in a format that is smaller than its previous format so that it takes up less space. There are two types of data compression: lossless compression and lossy compression. Lossless compression is compression where all of the original data is maintained and when uncompressed is all still there. Lossy compression is compression that gets rid of non-essential data, only keeping data that is vital to maintain the meaning of the file to make even smaller file sizes possible. A quick and basic example of compression would be run length encoding. This is where a string of letters is compressed by placing a number in the final encoded data in front of a letter to show how many of that letter follow said number. This only works well on strings where there are a lot of sequentially repeated letters, such as in this example, or also it would be possible that the final file size could be larger than the original. We see in the example shown that we can compress the size of this string by 54%, and it is easy to see how we could uncompress the data or just read it as is in this format. Why is compression important? If we lived in a universe that had unlimited file storage space, unlimited processing speed, and unlimited internet speeds, it wouldn't matter. However, since we don't exist in that universe, it is vital to keep file sizes low to fit on the storage space we have available to us and to make it easy to process. Additionally, a potentially more important reason would be for sending files over the internet. Sending large files over the internet takes a long time, so a smaller file would be able to be sent much faster. This applies in particular to streaming video, where if we were to send uncompressed video across the internet, it would be almost impossible to have live streaming, as the amount of data per frame would be so large it would just be impractical.
The first type of compression method is lossless compression. The goal of lossless compression is to reduce the file size without losing any information in the process. Lossless compression typically utilizes redundancy in the information as a way of encoding the data. Some common strategies employed to achieve lossless compression are Huffman encoding, the LZ77 method, deflate, and run length encoding. Now, the underlying method for almost all lossless compression algorithms is some variation or inclusion of Huffman and LZ compression. Deflate is an example and is commonly used for image compression or audio compression, with PNG and FLAC being the example. And you should already be familiar with run length encoding from earlier. Now we are going to take a more in-depth look at Huffman coding. A Huffman tree is built by taking a stream of data, in this case a sequence of characters, and uses the frequency at which each piece of data appears in the stream to rank them from most important to least important. To actually build the tree, we begin by taking two letters with the lowest frequency. We then create a node for each and join those nodes together at a parent node, which stores the combined frequency of the letters. So, for the current example, S and H are the least frequent letters, and we can see that they are joined by a node holding the value 2, meaning S and H appear a combined 2 times for the data from which this tree was built. This process continues until all the values have been assigned to a node in the tree. Once the tree is complete, the root node will store the total number of letters that the original string had. An important thing to know when encoding or decoding a piece of information is that going left down the tree is represented by a 0, and going right is represented by a 1. To decode something encoded with the Huffman tree, you simply use the given code to follow the branches of the tree until you reach a node containing data. For instance, if we are given the code 0, 1, since the first bit is 0, we would go left. Then, since the next bit is 1, we would continue right, at which point we would have arrived at the node containing the letter U. So, we now have that 0, 1 is U. This can be applied to longer strings of characters. For instance, when we use this Huffman tree to decode the sequence 1, 1, 0, 1, 0, 0, 0, 0, 0, 1, 1, 0, we get the string hummus. If we use ASCII to store the word hummus, we get that it requires 6 bytes or 48 bits of information, while our Huffman encoded version only needs 12 bits. As you can see, a Huffman tree is specific to the data that it encoded. This means that we could not encode the word apple using this Huffman tree, as none of its nodes contain the necessary letters. And likewise, we cannot decode something that was encoded using a different Huffman tree. The way in which lossless compression methods can be applied is almost limitless. However, these are some of the more common applications for The way in which lossless compression methods can be applied is almost limitless. However, these are some of the more common applications for the lossless compression method. PNG and SVGZ files are both image files which are compressed using the deflate method, which is a combination of LZ77 and Huffman. An example of lossless compression in audio files is the FLAC file. FLAC files can be compressed by up to 80% without seeing any decrease in audio quality.
To answer the question, how much data can we afford to lose, we must talk about lossy compression. First, let's look at the strategies in lossy compression. A discrete cosine transform, aka DCT, are used to convert data into summation of a series of cosine waves oscillating at different frequencies. Also, this algorithm is highly scalable. The data first shifted into the frequency domain, then depending on how much compression is required, the higher frequency coefficients of the signal are masked off and removed. The data can be recreated with the new coefficients, and the higher frequency are not present. DCTs are important to lossy compression of both audio and images, such as MP3 and JPEG. One of the well-known video format is MPEG-2. MPEG-2 video compression algorithm achieves very high rates of compression by exploiting the redundancy in video information. It removes both the temporal redundancy and the spatial redundancy, which are present in motion video. As for the application of lossy compression, JPEG utilizes DCT in a little bit more complicated way. Rather than simply removing the higher frequency coefficients of DCT matrix, the frequency coefficients are scaled by a quantization matrix. This matrix scales each coefficient by a numeric term. This quantization matrix is pre-calculated and defined by the JPEG standard and naturally favors the items in the top left corner of the matrix, which is a more frequency significant terms. The MPEG-2 video uses its own compression algorithm. As the picture shown, the temporal redundancy arises when successive frames of video display images of the same scene, whereas the spatial redundancy occurs because paths of this picture are shown replicated within a single frame of video. Therefore, compression may be performed by selectively discarding some of the redundant information. Now, as for the question, how much data can we afford to lose? Since most of the lossy compression are highly scalable, therefore, user can define any amount of data to lose according to what quality they desire.